So a steering tie rod connects the steering rack to the knuckle. It translates the rotational movement from the steering wheel to the tires, which allows you to turn the car. And it's also important in setting the toe angle of the tires. A steering tie rod will connect to the knuckle from, the right knuckle to left knuckle, and a drag link will connect the steering rack to the steering tie rod. So the first thing to consider when designing a tie rod is the safety loads, which will be the ultimate push-out, pull-out loading of a ball stud, the ultimate radial loading of the ball stud, and then the fatigue loading on all the studs and the connection rod. So first we want to consider all the main loading and make sure the part will stay intact. And then from there we look primarily at the joint design to figure out, the interaction between the ball and the polymer race or the ball and the metal race, and figure out the sealing, how it will seal at all angles in the application. And from there we go on to, appearance, corrosion resistance, and things like that. So off-highway tie rods are more high performance and high articulation. That's probably the biggest difference, is the articulation is really big because you have big suspension travel in side-by-sides. So what this means is the joints have to be able to slide a lot inside the housing without too much wear. And the sealing, the boot has to be able to handle a lot of different angles and keep the part maintained. At the same time, those type of joints are the ones that are going into muddy conditions, maybe fully submerged in mud. So the sealing is really important for those. And forklift tie rods, agriculture tie rods will tend to be a little heavier, bulkier, more serviceable. Weight is not as important of an aspect to consider when designing those. You just look for big safety factors so the part can handle loading. So the tie rod is important to control the wheel alignment of the vehicle, particularly the toe angle. And this toe angle helps the vehicle maintain its path without, wobbling too much. The stiffness of the steering tie rod is also important to control the vehicle, because if you want more feedback, you need to have a stiffer connection from the steering wheel to the wheels. And then if there's a loose joint or there's some wear in the joint, the feedback the driver will feel will be less, and they'll feel more wobble. It'll also be hard to keep the vehicle straight or keep it where you want to go when there's too much looseness in the steering tie rod. So to ensure minimal play, the first thing we would do is make sure to preload the joint. If it's metal to metal joint, preload it with maybe a washer or some sort of mechanism. And then if it's a polymer joint, we'll make sure the assembly process, we are preloading the joint to take away all the play. And then in the actual application process, we need to make sure the stress on the raceway, the stress on the ball is not exceeding the material properties. We need to consider the amount of cycles needed. And we also need to consider the grease interaction with the raceway, with the ball, and the sealing performance to make sure nothing get at the joint. So that kind of all combines to make sure even when we manufacture the joint, it's not going to have too much play or clearance, and then in the actual application, it's not going to gain too much play or clearance. I said before, the ultimate loading, the fatigue loading is very important, and that's what we consider first for safety. But in the actual design of the steering tie rod, I would say that's one of the easiest things to validate. We can make sure it's good right away with lab testing. So we end up spending a lot of time on the sealing because there's dynamic conditions in the environment and angles of the joint. So we need to make sure that we can keep it sealed at all angles. We also spend a lot of time tuning in the buckling loads to make sure the steering rack won't get damaged by too high of a buckling load, and to make sure the buckling load is good enough to meet the minimum requirements. And we also look at the joint internally to reduce wear, increase the torque consistency, and make sure the sealing is great. One of the main things to do is to make sure you reduce machining wherever possible. For the housing forgings, it's best to, reduce the machining from as many of those surfaces as possible. For the connection rod, if you're using one, the tube or the bar, reduce machining on that part. It's good to do FEA for topology to make sure you're not adding too much material in places that you don't need it. And then internally in the joint, there's a difference in cost for different polymers, and we will have to consider if we can use a lower cost one. And then something else that can be done is to remove corrosion resistance requirements from parts that are completely sealed. Sometimes the inner housing of the joint is completely sealed in a boot, and we can remove the corrosion resistance coating on parts like those to reduce the cost as well. Most common reason to alter design, I would say, from OEMs would be excessive wear or play in the joints early in the life before it meets the application requirements. Something else we get a lot would be if they're keeping the vehicle platform, maybe they're making the tires bigger, making the vehicle have more horsepower, but they don't necessarily want to change the steering setup. They want to keep the geometry of the steering the same. So, basically increase the loading for the same space constraint. That's a big one we will get. There's some other ones like reducing weight, increasing corrosion resistance, lowering cost, increasing the performance. So there's just some of the examples of things we might get to look at from OEMs. In general, all steering tie rods will be customized to an extent because there's not really a standard, design catalog size for steering tie rods. But then when you look at them, the connection to the knuckle, the connection to the steering rack, the length, the appearance, the inner materials, polymer, metal, are all different ways that we customize the tie rod to meet the exact specs of the OEM. Yeah. So normally for the ball studs, we use chrome moly steel or alloy steel that has very good heat treatability and very good elongation and toughness to withstand high fatigue life. The housings will generally be similar materials. Sometimes carbon steel can be used, but generally we stay with the high fatigue materials because it's a very critical application and there's a lot of cyclic loading on the ball stud. For the heavy duty equipment, one of the main criteria is just a very high safety factor. I said before, the weight is not the most critical thing in these parts, so you're designing a high safety factor part. You also, in a lot of these applications, you need to consider the serviceability of them. It needs to be easy to service, easy to replace if needed, easy to maintain, and the articulation angle is also smaller. So in these type of applications, you'll see much smaller articulation angles as well. On the actual parts itself, the first thing we will look at is the plating or the paint to make sure there's high corrosion resistance. Whether we use zinc nickel, eco powder coat, depending on the customer's expectations for the appearance and the corrosion performance. And then the joint is generally sealed with some sort of boot to keep out any contamination from the joint. That's really important. Depending on the articulation angle required by the vehicle and the application, we will change the design of the seal. We also need to consider, in some vehicles, the seal may be taking on more impacts from, debris on the ground, and sometimes the front seal is a little more hidden by the knuckle or something. So we'll consider all the geometry, but, most importantly, we want to make sure it's sealed in the exact application. And something else that we also pay attention to is you'll see sometimes there'll be joints with some, little area where debris or where water can build up into, and we want to make sure wherever we can, we design the part so water will kind of shut off it and it won't accumulate inside the joints. The studs, the most effective treating is zinc nickel. You can look at some non-electroplated zincs, like zinc flake, if you don't want to worry about hydrogen embrittlement. And then for the, connection rod or anywhere where it can be painted or e-coated, e-coating is generally the best performance for this corrosion resistance in these applications. The most common failure mode not considered by the engineers in design, I would say, would just be loose joints, whether it be too much play in the axial direction, radial direction, or both. And I would say the most common cause of that will be the sealing of the joint. If the joint is used in a vacuum to loading that it was designed to, it's probably rarely going to have too much play. It was designed to take those loads. But when you start to introduce the environment, the salt water, the mud water, the temperature changes, the humidity changes, the ozone changes, you introduce all those things to the part, and it makes a very tough life for the seal. So I would say the most common failure with steering tire rod would be the seal failing, leading to debris getting in, contaminating the grease, and then you get too much play. And that can be felt by the driver by having a hard time controlling the vehicle, and also just feel some looseness, some backlash from the steering wheel. To validate the tire rod extreme conditions, the best thing is always a field test. But when we look at the lab testing, we'll do it a few different tests in parallel. We will do fatigue testing of all the studs, of all the connections, to make sure they can withstand the cyclic loading nature of the joint. Then we'll look specifically at the seal performance with temperature changes, with humidity changes, and with the salt spray and a mud spray. And then we also look at the puncture resistance of the seal. Make sure something that may hit it in the application, contacts it in the lab, that it will stay intact. And then we also do ozone testing and material testing of the seal on its own. In tire rod technology, I would say a lot of what we look at is the polymer interaction with the ball. There's been a lot of research on seals and different ways to use different materials to, have the toughness required for all different types of environments. But we also pay a lot of attention to the different polymer materials, the different additives you can put into the polymer materials to increase the life. I think we talked a little bit about some of the joints that, they're going into bigger vehicles, but the space envelope isn't really getting any bigger. So, while the requirements are getting bigger, we need to look at ways to increase the life and durability of our joints. And one of the best ways we can do that is through the different materials, because it doesn't require us to take up more space. It doesn't significantly impact the cost. So that's what we look at to meet our customers' needs.